Testing 1 2 3. Testing 1 2 3. Just want to make sure everything is up and running well. Alright, this chapter is going to be a fair amount from what I remember. So I just want to make sure I properly get through it. So let's start with no delay. Chapter 5. Permutation groups. Permutation groups are central to the study of geometric symmetries and the Galois theory, the study of finding solutions of polynomial equations. They also provide abundant examples of non-abelian groups. Let us recall for a moment that the symmetries of the equilateral triangle delta ABC from Chapter 3. The symmetries actually consist of permutations of the three vertices, where a permutation of a set S equals ABC is a one-to-one and onto, called bijective also, map, pi from S to S. The three vertices have the following 6 permutations. We'll read this as ABC goes to ABC, ABC goes to CAB, ABC goes to BCA, ABC goes to ACB, ABC goes to CBA, ABC goes to BAC. We have used the array ABC to BCA to denote the permutation that sends A to B, B to C, and C to A. That is, A goes to B, B goes to C, C goes to A. And this will be a very standard thing. So I will write a quick reminder here. A is denoted as means pi of A equals B, pi of B equals C, and pi of C equals A. The symmetries of the triangle form a group. In this chapter, we will study all possible groups of this type. Chapter 5.1. Definition and notations. In general, the permutations of a set X form a group S sub X. If X is a finite set, we can assume that X is equal to 1, 2, all the way to n. Otherwise, if it's not labeled as that, we can just find a bijection that corresponds to that. And that bijection will allow us to transfer between permutations of the set from 1 to n and the set of whatever we're working with. In this case, we write S sub n instead of S sub x. The following theorem says that S sub n is a group. We call this the symmetric group on n letters. Theorem 5.1. The symmetric group on n letters, S sub n, is a group with n factorial elements, where the binary operation is the composition of maps. Proof. The identity of S sub n is just the identity map that sends 1 to 2, 2 to 2, 1 to 1, 2 to 2, and n to n. Every element is sent to itself. If f from Sn to Sn is a permutation, then f to the negative 1 exists, since f is one-to-one and onto, and hence has a unique inverse. Hence every permutation has an inverse. Compositions of maps is associative, which makes the group operation associative. We leave the proof that S sub n is equal, the order of S sub n is equal to n factorial as an exercise. This was actually covered, if I remember correctly, either in Chapter 3 or Chapter 4, one of the problems there. I'm pretty sure it was Chapter 4. A subgroup of S sub n is called a permutation group. Example 5.2. Consider the subgroup G of S sub 5 consisting of the identity permutation ID and the permutations sigma is 1 2 3 4 5 goes to 1 2 3 4 5, 1 2 3 4 5 goes to 3 2 1 4 5, and 1 2 3 4 5 goes to 3 2 1 5 4. The following table tells us how to multiply elements in the permutation group G. So we have, just for example, ID composed with sigma is sigma, ID composed with tau is tau, ID composed with mu is mu. We have things that way, and we generally just have a somewhat nice structure here. Just going to leave this a bit more on. I imagine for the reading questions, it will have us explicitly computing some of these permutations. So for now, I'm not going to actually compute this table and show why the table works as it does. Remark 5.3. Though it is natural to multiply elements in a group from left to right, functions are composed from right to left. Let sigma and tau be permutations on a set X. To compose sigma and tau as functions, we calculate sigma composed with tau of X is equal to sigma tau of X. That is, we do tau first, then sigma. There are several ways to approach this inconsistency. We will adopt the convention of multiplying permutations right to left. So, sigma tau of X is equal to sigma of tau of X. To compute sigma tau, do tau first and then sigma. That is, tau sigma of X, we mean sigma of tau of X. Another way of solving this problem would be to write functions on the right. That is, instead of writing sigma of X, we could write X of sigma. We could also multiply permutations left to right to agree with the usual ways of multiplying elements in a group. Certainly all of these methods have been used. I will say that it is standard to have the function composition notation, although there is alternative notations used. It's not common anymore, in my experience. Example 5.4. Permutation multiplication is not usually commutative. Let sigma be equal to 1, 2, 3, 4, gets sent to 4, 1, 2, 3, and tau is equal to 1, 2, 3, 4, gets sent to 2, 1, 4, 3. Then sigma tau is equal to 1, 2, 3, 4 is sent to 1, 4, 3, 2, but tau sigma equals 1, 2, 3, 4 is sent to 3, 2, 1, 4. Cycle notation. The notation that we have used to represent permutations up to this point is cumbersome, to say the least. To work effectively with permutation groups, we need a more streamlined method of writing down and manipulating permutations. A permutation sigma in SLS sub X is a cycle of length k. If there exist elements a1, a2, all the way to ak in X, such that sigma a1 equals a2, sigma of a2 equals a3, all the way to sigma ak is equal to a1. So, one way of saying this, I'm going to write the board. We have a1 is sent to a2, is sent to a3, is sent to on and on, is sent to ak, is sent back to this by composition with by application of sigma, and otherwise is fixed. We will write a1, a2, ak to denote the cycle sigma. Cycles are the building blocks of all permutations. So in this case, let me do this, bring this up a little bit. This implies that we write sigma as a1 is sent to a2, a2 is sent to a3, on and on up to ak. And here we close the brackets, which means that from here, ak goes back to a1 under the permutation. Example 5.5. The permutation sigma equals 1, 2, 3, 4, 5, 6, 7 is 6, goes to 6, 3, 5, 1, 4, 2, 7 equals 1, 6, 2, 3, 5, 4. For this, notice that 1 goes to 6. Oh gosh. 1 goes to 6, so we have 1 followed by 6 in this representation. Then 6 goes to 2, so we have 6 and then 2 in this. Then 2 goes to 3, so we have 2 and 3 in this. Then 3 goes to 5, so we have 3 and 5 in this. 5 goes to 4, so we have 5 and 4 in this. And then 4 goes back to 1, so we close the brackets. Is a cycle of length 6. Whereas tau equals 1, 2, 3, 4, 5, 6 to 1, 4, 2, 3, 5, 6 equals 2, 4, 3 is a cycle of length 3. Notice here that if we don't include something on this, we mean that it's fixed. So for example, this only includes symbols 2, 4, 3. What happens with symbols 1, 5, and 6? Well, 1 is sent to 1, 5 is sent to 5, and 6 is sent to 6. If they're an identity, if they functionally don't give us any new information on the permutation, we leave them out of the cycle notation. Not every permutation is a cycle. Consider the permutation 1, 2, 3, 4, 5, 6 goes to 2, 4, 1, 3, 6, 5, which is equal to the cycle 5, 6 composed with the cycle 1, 2, 4, 3. This permutation actually contains a cycle of length 2 and a cycle of length 4. Alright, first, to see this, notice 5 goes to 6, 6 goes to 5. So we have 5 and 6 on the outside here. Then 1 goes to 2, 2 goes to 4, 4 goes to 3, and 3 goes back to 1. So we then have this 1, 2, 4, 3. And actually, because these cycles are disjoint, we could write them any ways, like any two different ways. Example 5.6. It is very easy to compute products of cycles. Suppose that tau is equal to 1352, sigma is equal to 1352, and tau is equal to 256. If we think of sigma as 1 goes to 3, 3 goes to 5, 5 goes to 2, 2 goes to 1, and tau as 2 goes to 5, 5 goes to 6, 6 goes to 2, then for sigma tau, remembering that we first apply tau and then sigma, it must be the case that 1 goes to 3, 3 goes to 5, 5 goes to 6, and then 6 goes to 2, but then 2 goes to 1. So sigma tau is equal to 1356. If mu is equal to 1634, then sigma mu is equal to 165234. Even if it doesn't explicitly have any exercises of computations like this later on, I'll do more of these just to get more exposure with cycle notation, because it's a very powerful tool, but it literally only shows you everything you need and nothing else. So it can be a lot. Alright, two cycles in sigma in Sx. Sigma equals A1, A2 to AK, and tau equals B1, B2 to BL are disjoint if AI is not equal to BJ for all valid I and J. Example 5.7. The cycles 1, 3, 5 and 2, 7 are disjoint. However, the cycles 1, 3, 5 and 3, 4, 7 are not. Notice here that 3 is in both these cycles, which means using the previous definition, we have A2 is not equal to is equal to B1, so they're not disjoint. Calculating their products, we find that 13527 is equal to 13527, but 135347 is equal to 13475. The product of two cycles that are not disjoint may reduce to something less complicated. The product of disjoint cycles cannot be simplified. Proposition 5.8. Let sigma and tau be two disjoint cycles in S sub x. Then sigma tau is equal to tau sigma. So for specifically disjoint cycles, they are commutative under function composition. Proof. Okay, wait, before I do the proof, give me a second to grab a drink of water. Alright, proof. Let sigma equals A1, A2 to AK, and tau is equal to B1, B2, BL. We must show that sigma tau of x equals tau of sigma of x for all x. If x is neither in A1, A2 up to AK, nor B1, B2 up to BL, then both sigma and tau fix x. That is, sigma of x equals x and tau of x equals x. And hence, sigma tau of x equals sigma of tau of x equals sigma of x equals tau of x equals tau of sigma of x equals tau of sigma of x. Do not forget, in this case, when we have the expression here, we then first evaluate this, and then evaluate that. We have this, and then we evaluate this, and then this. It is important to remember that we are multiplying permutations right to left, which is the opposite of order in which we usually multiply group elements. Now, suppose that x is an A1, A2 to AK. Then sigma of AI is equal to A I mod k plus 1. That is, A1 goes to A2, A3 goes to A2 goes to A3, all the way to AK minus 1 goes to AK, and AK goes to A1. It's a complicated modular way of representing this diagram right here. However, tau AI is equal to AI since sigma and tau are disjoint. Therefore, sigma of tau of AI equals sigma of tau of AI equals sigma of AI equals A I mod k plus 1 equals tau of A I mod k plus 1 equals tau of sigma of AI equals tau of sigma of AI, or tau sigma of AI. Similarly, if x is in B1, B2 up to BL, then sigma and tau also commute. For this, we would literally just replace the AI by BJ. Theorem 5.9. Every permutation in Sn can be written as the product of disjoint cycles. Proof. We can assume that x is equal to 1, 2, all the way up to n. If sigma is in Sn, and we define x sub 1 to be sigma 1, sigma squared at 1, on and on, then the set x1 is finite, since x is finite. Now, let I be the first integer in x that is not in x1, and define x2 by sigma I, sigma squared I, on and on. Again, x squared is a finite set. Continuing in this manner, we can define finite disjoint sets x3, x4, on and on. Since x is a finite set, we are guaranteed that this process will end. This is a very important part. And there will only be a finite number of these sets, say R. If sigma I is a cycle defined by sigma I of x is equal to sigma x with x and x on I, x of I, or x is for x not in xi, then sigma equals sigma 1, sigma 2, all the way up to sigma R. Since the sets x1, x2 up to xr are disjoint, the cycles sigma 1, sigma 2 up to sigma R must also be disjoint because they only swap elements in the disjoint sets. Example 5.10. Let sigma equals 1, 2, 3, 4, 5, 6 is sent to 6, 4, 3, 1, 5, 2, and tau is equal to 1, 2, 3, 4, 5, 6, 2, 3, 2, 1, 5, 6, 4. Using cycle notation, we can write sigma is equal to 1, 6, 2, 4. Tau is equal to 1, 3 multiplied by 4, 5, 6, which tells us that sigma tau is equal to 1, 3, 6 times 2, 4, 5, and tau sigma is equal to 1, 4, 3 times 2, 5, 6. Remark 5.11. From this point forward, we will find it convenient to use cycle notation to represent permutations. When using cycle When using cycle notation, we will often denote the identity permutation by 1. So 1 equals ID. Transpositions. The simplest permutation is a cycle of length 2. Such cycles are called transpositions. Since a1, a2, all the way to an is equal to a1, an, a1 n minus 1, all the way to a1, a3, a1, a2, any cycle can be written as a product of transpositions, leading to the following proposition. So for this, to show this, because I kind of just breezed through here in a way that I personally don't like and left me confused for a while, notice, we evaluate from right to left. So first, a1 is sent to a2. Now, a2 is then sent to a1. So a1, which is now a2, is actually, wait, okay. A1, a2, all the way up to a to the n, if they used these a to the n, is equal to a1, a n, to a1, a3, a1, a2. So first, evaluating this, a1 is sent to a2, right? But then a2 is sent to a1. So like a2 is sent to a1. But then, since it's now in a1, it passes to this thing and is sent to a3. So is sent to a3. Then, similarly, a3 is sent to a1, which would be sent to a4, which would be sent to a1, which would then be sent to a4. So a3 is sent to A1 is sent to A4. And generally, let me just lift this up a little bit. Generally, we have that A sub n minus 1, or actually, I'll use A sub k. A sub k minus 1 is sent to A sub 1, is then sent to A sub k under this, which ultimately means that A sub k minus 1 is sent to A sub k. Proposition 5.12. Any permutation of a finite set containing at least two elements can be written as the product of transpositions. Example 5.13. Consider the permutation 1,6 equals 253 is equal to 162325 is equal to 1645234525. As we can see, there is no unique way to represent permutations as the product of transpositions. For instance, we can write the identity permutation as 1, 2, 1, 2, since 1 would be sent to 2, then 2 would be sent to 1, and 2 would be sent to 1, and then 1 would be sent to 2. Or 1, 3, 2, 4, 1, 3, 2, 4, and in many other ways. However, as it turns out, no permutation can be written as the product of both an even number of transpositions and an odd number of transpositions. For instance, we could represent the permutation 1,6 by 2,3, 1,6, 2,3, or by 3,5, 1,6, 1,3, 1,6, 1,3, 3,5, 5,6. But 1,6 will always be the product of an odd number of transpositions. Alright, here we go. Lemma 5.14. If the identity is written as the product of R transpositions, ID equals tau 1, tau 2, up to tau R, then R is an even number. Proof. We will employ induction on R. A transposition cannot be the identity. Hence, R is greater than 1. If R equals to 2, then we are done. Suppose that R is greater than 2. In this case, the product of the last two transpositions, tau R minus 1, tau R, must be one of the following cases. Either AB is equal to ID, BC, AB is equal to AC, BC, CD, AB is equal to AB, CD, or AC, AB is equal to AB, BC, where A, B, C, and D are distinct. The first equation simply says that a transposition is its own inverse. If this case occurs, delete tau R minus 1, tau R from the product to obtain ID is equal to tau 1, tau 2, all the way up to tau R minus 3, tau R minus 2. By induction, R minus 2 is even. Hence, R must be even. So, I'm going to just double check that step because that step was very subtle. And also just to make sure I properly, don't downplay how big that one is. So in this case, we have actually, wait, no. I don't know if we necessarily require it to be ID, right? Yeah, okay. Actually, okay. So ID is equal to tau 1, tau 2, all the way up to tau R. We assume in this case that tau R minus 1 tau R is equal to AB. But notice that this is just equal to ID, because A will be sent to B, but then B will be sent to A, and likewise for B. B will be sent to A, and then A will be sent to B. So ID equals tau 1, tau 2, all the way up to tau R minus 2, tau R minus 1, tau. However, this we already know is ID, so we know that it will just be equal to tau 1, tau 2, all the way up to tau R minus 2, which by the inductive hypothesis we know is just the product of transpositions, an even number of transpositions. And since R is equal to R minus 2 plus 2, we know that if R minus 2 is even, then R is even. Alright, in each of the other three cases, we can replace tau R minus 1, tau R, with the right-hand side of the corresponding equation to obtain a new product of R transpositions for the identity. In this new product, the last occurrence of A will be in the next to the last transposition. We can continue this process with tau R minus 2, tau R minus 1, to obtain either a product of R minus 2 transpositions, or a new product of R transposition where the last occurrence of A is in tau R minus 2. If the identity is the product of R minus 2 transpositions, then again we are done by our inductive hypothesis. Otherwise, we will repeat some procedure with tau R minus 3, tau R minus 2. At some point, either we will have two adjacent identical transpositions canceling each other out, or A will be shuffled so that it appears only in the first transposition. However, the latter case cannot occur because the identity would not fix A in this instance. Therefore, the identity permutation must be the product of R minus 2 transpositions, and, again by our inductive hypothesis, we are done. Alright, so, basically, with any transposition in the form of this, notice that we take this, and we just move it to a transposition, with A being at the front. We are able to take A, if A is in position, like, if we have ID is equal to tau 1, tau 2, up to tau R, if we have A being in the representation for this, we can move A to tau R minus 1. And then we can continue on eventually until we have tau 1. Now, at any point, we know basically there are two cases. Either at some point we get a proposition that cancels out, and we can use the previous logic to erase 2 and take it to the ID, or A goes to tau 1. But if A goes only to tau 1, then that means A is not fixed in place. We don't have the identity, which would imply identity is not equal to identity, which is literally just not true. So therefore, we must have a case where we have a pair that cancels out on the process of getting there. Alright. Yeah. Alright, oh yeah, the link to the textbook's in the description. Yeah, if you have any questions on this proof and want to just work out a few examples by hand, here, page 75. Because it's a kind of subtle trick, and it's a bit more of an inductive step than is used to. Instead of just showing that a certain property about something holds, we have an algorithm that by induction and finiteness restrictions, note that it's both, must terminate. Alright, moving on though. Theorem 5.15. If a permutation sigma can be expressed as the product of an even number of transpositions, then any other product of transpositions equaling sigma must also contain an even number of transpositions. Similarly, if sigma can be expressed as the product of an odd number of transpositions, then any other product of transpositions equaling sigma must also contain an odd number of transpositions. Proof. Suppose that sigma is equal to sigma 1, sigma 2 up to sigma m is equal to tau 1, tau 2 up to tau n, where m is even. We must also show that n is an even number. The inverse of sigma is tau m to tau 1. Since ID is equal to sigma m, all the way up to sigma 1, is equal to tau 1, tau m up to tau n, sigma m, all the way up to sigma 1. N must be even by lemma 5.14. The proof for this case in which sigma can be expressed as an odd number of transpositions is left as an exercise. In light of theorem 5.15, we define a permutation to be even if it can be expressed as an even number of transpositions, and odd if it can be expressed as an odd number of transpositions. Alright, give me a second. While I grab a drink, reminder that the main thrust here is that because it's transposition, we can basically just reverse all the transpositions. Take that product, show that it's ID, and then apply the previous lemma along with what we know about m being even to conclude that n is even, which is actually going to be the same thing for if it's odd, because it's going to be m plus n total transpositions, and if m is even, then n must be even for m plus n to be even, and if m is odd, n must be odd for m plus n to be odd. The alternating groups. One of the most important subgroups of S sub n is the set of all even permutations A sub n. The group A sub n is called the alternating group on n letters. Theorem 5.16. The set A sub n is a subgroup of S sub n. Proof. Since the product of two even permutations must also be an even permutation, A sub n is closed. The identity is an even permutation and therefore is an A sub n. If sigma is an even permutation, then sigma equals sigma 1, sigma 2 up to sigma r, where each sigma I is a transposition and r is even. Since the inverse of any transposition is itself, sigma to the negative 1 equals sigma r minus 1 up to sigma 1 is also an A sub n. Excuse me. Please scroll up. Book. Okay. Proposition 5.17. The number of even permutations in S sub n for n greater than or equal to 2 is equal to the number of odd permutations. Hence, the order of A sub n is n factorial over 2. Proof. Let A sub n be the set of even permutations in S sub n, and B sub n be the set of odd permutations. If we can show that there is a bijection between these sets, they must contain the same number of elements. Fix a transposition sigma in Sn, any transposition. Since n is greater than or equal to 2, such a sigma exists. Define lambda sigma from an to bn by lambda sigma of tau equals sigma tau. Think of this as literally just being a fancy notation to mean this function takes an even permutation and just slaps on just another transposition to it. Suppose that sigma tau lambda sigma of tau equals lambda sigma of mu. Then sigma tau is equal to sigma mu, and so tau is equal to sigma minus 1 sigma tau is equal to sigma minus 1 sigma mu is equal to mu. Therefore, sigma lambda sigma is 1 to 1. We will leave the proof that lambda sigma is surjective to the reader, which will, I know if you're like unsatisfied with this, there's also, when we're talking about the Cayley table theorem, oh god, I forget what the table is specifically called, but there will be another proof of this fact when it's talking more so about cosets and like subgroups being defined in parts by permutations and being subsets of permutation groups. So there is part of a fuller response later in the book, but I definitely recommend like working through this on your own time. It is a good exercise to just like make sure you're really comfortable with a lot of the group stuff. Example 5.18. The group A sub 4 is a subgroup of S sub 4 consisting of even permutations. There are 12 elements in A sub 4. 1, 1, 2, 3, 4, 1, 3, 2, 4, 1, 4, 2, 3, 1, 2, 3, 1, 3, 2, 1, 2, 4, 1, 4, 2, 1, 3, 4, 1, 4, 3, 2, 3, 4, and 2, 4, 3. One of the end of chapter exercises will be to write down all the subgroups of A4. You will find that there is no subgroup of order 6. Does this surprise you? Oh, that's gonna be a big thing. Okay. Historical note. Lagrange first thought of permutations as functions from a set to itself, but it was Cauchy who developed the basic theorems and notations for permutations. He was the first to use cycle notation. Augustin Louis Cauchy, born 1789, died 1857, was born in Paris at the height of the French Revolution. His family soon left Paris for the village of Arcueil, apologies for the mispronunciation, to escape the Reign of Terror. One of the family's neighbors there was Pierre-Simon Laplace, 1749 to 1827, who encouraged him to seek a career in mathematics. Cauchy began his career as a mathematician by solving a problem in geometry given to him by Lagrange. Cauchy wrote over 800 papers on such diverse topics as differential equations, finite groups, applied mathematics, and complex analysis. He was one of the mathematicians responsible for making calculus rigorous. Perhaps more theorems and concepts in mathematics have the name Cauchy attached to them than of any other mathematician. Okay. Dihedral groups, section 5.2. Another special type of permutation group is the dihedral group. Recall the symmetry group of an equilateral triangle in chapter 3. Such groups consist of the rigid motions of a regular n-sided polygon or an n-gon. For n equals 3, 4, on and on, for arbitrarily large values of n, we define the nth dihedral group to be the group of rigid motions of a regular n-gon. We will denote this group by d sub n. We can number the vertices of a regular n-gon by 1, 2, all the way up to n, which we have in this example here. Notice that there are exactly n choices to replace the first vertex. If we replace the first vertex by k, then the second vertex must be replaced either by vertex k plus 1 or by vertex k minus 1. Hence, there are 2n possible rigid motions of the n-gon. We summarize these results in the following theorem. Theorem 5.20. The dihedral group d sub n is a subgroup of S sub n of order 2n. And we think of it as a subgroup in the sense of labeling the vertices of the n-gon by the same elements that you would label the sets in the elements of the permutation group. Theorem 5.21. The groups d sub n for n greater than or equal to 3 consist of all products of the two elements r and s, satisfying the relations r to the n is equal to 1, s squared is equal to 1, and srs equals r to the negative 1. Also note, here we're assuming r and s to be non-trivial, and we are assuming r to this to be defining the order of r. There is some intentional ambiguity for clarity of explanation in this. For example, rs and srs, everything being equal to the identity, is technically a valid satisfication of the groups. But that's not what it actually is. So, proof. The possible motions of the regular n-gon are either reflections or rotations. Figure 5.22. There are exactly n possible rotations given by ID, or 0 times 360 over n, 360 over n, 2 times 360 over n, all the way up to n minus 1 360 over n. We will denote the rotation 360 over n by r. The rotation r generates all the other rotations. That is, r to the k is equal to k times 360 degrees over n. Label the n reflections s1, s2, up to Sn, where S sub k is a reflection that leaves vertex k fixed. If there are two cases of reflections, depending on whether n is even or not odd. For example, they don't have it good in this one. So in this case, because we have an even number of vertices, we have the reflection going through 1 and 5, fixing both 1 and 5. Otherwise, it would only fix one of them. Think about this triangle and flipping it over this line of symmetry. If there are an even number of vertices, then 2 vertices are left fixed by a reflection, and S1 equals Sn plus over 2 plus 1. S2 is equal to Sn plus over 2 plus 2, all the way to Sn over 2 is equal to Sn. If there are an odd number of vertices, then only a single vertex is left fixed by a reflection, and S1, S2, up to Sn are distinct. In either case, the order of each Sk is 2. Let S equals S1. Then S squared is equal to 1, and R to the n is equal to 1. Since any rigid motion of T of the n-gon replaces the first vertex by the vertex k, the second vertex must be replaced by either k plus 1 or by k minus 1. If the second vertex is replaced by k plus 1, then T equals R to the k, If the second vertex is replaced by k minus 1, then t is equal to r to the k s, s squared. Hence, r and s generate d sub n. That is, d sub n consists of all finite products of r and s. dn is equal to 1, r squared, up to rn minus 1, s, rs, r squared s, all the way up to r to the n minus 1 s. We will leave the proof that SRS is equal to r to the negative 1 as an exercise. Figure 5.23. Types of reflections of a regular n-gon. Oh yeah, we see in the example of the odd case, it would only fix 1 over this. Example 5.24. The group of rigid motions of a square, D4, consists of 8 elements, with the vertices numbered 1, 2, 3, and 4. The rotations are r is equal to 1, 2, 3, 4, r squared equals 1, 3, 2, 4, r cubed is equal to 1, 4, 3, 2, and r to the 4th equals 1. And the reflections are s1 equals 2, 4, and s2 is equal to 1, 3. The order of d4 is 8. The remaining 2 elements are rs1 is equal to 1, 2, 3, 4, and r cubed s1 equals 1, 4, 2, 3. Note as well, since we are in an abstract group, we will adopt the convention that group elements are multiplied left to right instead of functions. Because we multiply a rotation by something, and we think of these rotations as being things instead of actions. So we go back to our normal left to right multiplication. So in this case, r is equal to, oh I know, associativity, yeah, it doesn't really matter in that case. Yeah, my apologies, okay. The motions of a cube. We can investigate the groups of rigid motions of geometric objects other than a regular n-sided polygon to obtain interesting examples of permutation groups. Let us consider the group of rigid motions of a cube. By rigid motion, we mean a rotation with the axis of rotation about opposing faces, edges, or vertices. One of the first questions that we can ask about the group is, what is its order? A cube has 6 sides. If a particular side is facing upwards, then there are 4 possible rotations of the cube that will preserve the upward-facing side. Hence, the order of the group is 6 times 4 equals 24. We have just proved, in fact, the following proposition. The group proposition 5.26. The group of rigid motions of a cube contains 24 elements. Now, theorem 5.27. The group of rigid motions of a cube is S4. Now there's something subtle here. There's a notion not properly introduced called isomorphism, which means that any way that you label the motions of a cube, you will be able to find a bijective function that preserves the composition. You'll be able to basically rename the composition in the group law such that it looks like S sub 4. Proof. From proposition 5.26, we already know that the motion group of the cube has 24 elements, the same number of elements as there are in S4. There are exactly 4 diagonals in the cube. If we label these diagonals 1, 2, 3, and 4, we must show that the motion group of a cube will give us any permutation of the diagonals, figure 5.28. If we can obtain all these permutations, then S sub 4 and the group of rigid motions of a cube must be the same. To obtain a transposition, we can rotate the cube 180 degrees about the axis joining the midpoints of opposite edges, which is seen in figure 5.29. This right here. Oh gosh, it's lagging. If we obtain all the, yes, okay. There are 6 such axes, giving all transpositions in S4. Since every element in S sub 4 is the product of all of a finite number of transpositions, the motion group of a cube must be S4. Alright. Okay, we are nearly at the end of the reading questions. Let's go. Okay. Express 1, 3, 4, 3, 4, 5 as a cycle, or a product of disjoint cycle. So, it's going to be 1, 3, 5. 3, 5. Oh no, not 1, 3, 5. Oh no, 1, 3, 4. 1, 3, 4. 3, 5, 4. So let's check this out. Okay, so 1 doesn't interact with this first cycle. Then from this cycle, 1 is moved to 3. 3 is moved to 5, and 5 doesn't interact with this cycle, so 3 is just moved to 5. We have 4 is moved to 3, and then 3 is moved back to 4. So 4 is sent just to 4. Now 5 is sent to 4, and 4 is sent to 1. And since these 4 elements are the only elements moved by the permutation, so it's what we only have to care about in the cycle group, which means that we can express this as 1 goes to 3, 3 goes to 5, and 5 goes back to 1. And if we wanted to be, from here, fairly pedantic, we could also express this as you transposition 1, 5, 1, 3. Since 1 is sent to 3, and 3 is sent to 1, and then 1 is sent to 5, so 3 is sent to 5, and 5 is just sent back to 1. So for example, we would have this cycle 1 through 5 in A sub 5. Alright, let me clear out some of the space here. Yeah. Alright, what is a transposition? A transposition is a permutation that swaps simply 2 elements, A, B. What does it mean for a permutation to be even or odd? So any permutation can be expressed as some number of these transpositions. And that number will be invariant up to mod 2. So it will be invariant up to even or oddness. So we fundamentally call that representation even or odd. Let's grab another group that is fundamentally the same as A sub 3. Okay. So A sub 3, we have ID. We have 1, 2, 1, 3. Why no, it wouldn't be with ID. We have 1, 2, 2, 3. And 2, 3, 1, 2. In this case 2 is sent to 1, but in this case 2 is sent to 3. So this is like uniquely 1, 2, 2, 3. 1, 2, or 2, 3, 1, 2. So let's not worry about what ID does. Let's just worry about how these elements interact with each other. So 1, 2, 2, 3. If we add 1, 2, 2, 3 to it. Okay, first of all, let's note that these numbers are both ID. But then actually from here, just by the group elements. So like, let's compute also, make sure we're not missing anything. So A sub 3. A sub 3, the order of A sub 3, by previous proof, is 3 factorial over 2 is equal to 3, so it only has 3 elements. So otherwise, this is sent to 2, 3, 1, 2, and this is sent to 2, 3, 1, 2, 1, 2, 2, 2, 3. So if you notice, if we call this element 2 and this element 3, or no, actually that's not right for what I'm going for. If we call that 1, we call that 2. We call that 1, we call that 2. Then note that we have the table 0, 1, 2, 0, 1, 2, 0, 1, 2, 0, 1, 2, 2, 1, 0, 0, which is just the integers mod 3 in this case. Which also is like kind of funky, because this means we have, later on you'll learn, this means we actually have a field structure on this, which is kind of wild, but let's not worry about that too much right now. Okay. Right, yeah, some groups of pentagon. No. Alright, I think we're good. Alright. We are about to get to exercise central. There's a lot of good stuff here, especially later on. This is called, orbits are related very much to something called group actions. And those are going to be very valuable, especially to anyone doing like algebraic topology or differential geometry in future. You'll phrase a lot of your results of like either Lie groups or just like regular, it's vector bundles. Yes, I think it's vector bundles. It's like some group transitive orbit actions or something like that. Some G principal bundles, yes, for a topological group G. You'll phrase a lot of results in terms of that and group actions from that. So I will definitely be doing a lot of this. But until that, I'm going to grab myself a cup of coffee. So Okay, I'm back. Let's see. Double check that things are working. Oh gosh, this is gonna be a technical moment. Alright, let me try to go back to the standard scene to see if it updates. Oh gosh, okay. Give me a moment, this is being a whole thing. Alright, it looks like we are slowly coming back in. My internet is having a great time. My bitrate has gone from, unstable to being apparently perfectly fine. Don't know how that happens. I guess it just kind of does. We love to see it. Gosh, okay. Well, oh, it's still on the intermission thing. We're way past that. What is going on? Okay, so it's just extremely delayed. Alright, okay, let's just keep moving. So, I have a fun idea. And I'm going to work backwards. Actually, no, never mind. Okay, I'm gonna work starting from the top, go to like 10, and then work backwards. Because there's a lot of computational exercises that it's probably just gonna have nice to have down on the books. Okay, so 1, 2, 3, 4, 5 goes to 2, 4, 1, 5, 3. 2, 4, 1. First, we're gonna be writing some stuff in cyclic notation. So 1, 2, 3, 4, 5 goes to this. So we know 1 will go to 2, right? We know 1 goes to 2. 2 will go to 4. 4 will go to 5. 4 will go to 5. 5 will go to 3. And then 3 will go back to 1, so we'll be able to close it, and we have it written in cyclic notation nice and neat like this. I'll do, that's A. It's a similar thing, and because it's probably going to be a trick question for this one, I'm going to do D. 1, 2, 3, 4, 5. 1, 4, 3, 2, 5. Okay. 1, 4, 3, 2, 5. 1, 2, 3, 4, 5. Is going to be equal to, well, first, notice that 1 is sent to 1. So we don't need to write that in. We have that 2 is sent to 4. And then 4 is sent back to 2. And then both 3 and is sent to 3 and 5 is sent to 5. So it's actually just, literally just equal to this. Also showing a lot of the benefit of using cycle notation, because otherwise writing this would be a nightmare. Okay. So this was A, this was D. Alright, compute each of the following. I'll do A, B, P, and O. So 1, 3, 4, 5. 1, oh gosh. 1, 3, 4, 5 goes to 2, 3, 4. So let's think about this. Okay, so in this case, 4 is actually, let's start with the lowest value. Let's think about 1. 1 doesn't interact with this permutation, but 1 is sent to 3 in this. Now 3 is sent to 4, but then 4 is sent to 5. from here, 5 doesn't interact with this, but 5 is just sent back to 1 here, so we have a closed cycle. Then, the only one we're missing, 2 is sent to 3, and then 3 is sent to 4. And likewise, 4 is just sent to 2, and 2 doesn't interact, so we have that it is equal to this. So, A. This is A, right? Yeah, it's A, okay. Actually, I'll start putting the letters, like, up here. A, B, we have 1, 2, 1, 2, 4, 5, 3. 1, 2, 1, 2, 5, 3. For this, first of all, 1 is sent to 2, and 2 is sent to 1. So 1 actually is sent back to itself in this. We actually can't start at 1. So 2. 2 is sent to 5, and then 5 doesn't interact with that. So 2 is sent to 5, then 5 is sent to 3, then 3 is sent to 1, but then 1 is sent to 2, so we can just close off this cycle here. And you can actually compute the rest. It will just be this, and it will simplify down to this. Then next, we're going to be going way down. So we're going to be going, so we're going to be going 1, 2, 3, 4, 1, 2, 4, 7. 1, 2, 3, 4, 1, 2, 4, 7. 1, 2, 4, 7. All this to the -1. Well, this number will be the number such that when we multiply it by 1, 2, 3, 4, 1, 2, 4, 7 is equal to 2. So we just have, think about like a rightmost multiplication in this case. We have 4, 7, so it collapses, these two 4, 7s collapse. Then we have 1, 2. So these two collapse. Then 3, 4. So these two collapse. And then 1, 2. These two collapse. And then from here you can expand these as you so desire. But that is roughly how this will go in this case. And then finally, for P, I'm going to give a bit more space to P, because P is something where we can use a general method, and we can specifically use the fact that it's a group. So we have 1, 2, 3, 5, 3, 5, 4, 6, 7, 4, 6, 7 to the -1, which, using the fact that this is a group, is just 4, 6, 7 to the -1 times 1, 2, 3, 5 to the -1. So we just need to find the permutations that work for these. So the permutation, that will be the inverse. So this, first of all, this function sends 4 to 6. So its inverse will send 6 to 4. We then have 7 is sent to 4. So 4 will be sent to 7 for this. And then for this, we have 1 is sent to 2. So 2 is sent to 1. Then 5 is sent to 1. So 1 is sent to 5. Then 3 is sent to 5. So 5 is sent to 3. And it will be the composition of these as the inverse. So this will be the case for, I think it was P. A similar logic works for everything else. I just don't want to write it out in full detail because that would take forever. And there are much more interesting theoretic questions to approach here. Express the following permutations as product transition as identify them as even or odd. I'm going to be honest, I'm very lazy. So I guess something we can do to simplify this is that notice that a cycle of length k, a1, all the way up to, actually we'll call it an end cycle, is equal to A1, AN, all the way up to A1, A2. So notice that there are, in this, n minus 1 transpositions. So for example, well, let's analyze this monstrosity. So this is length 5, a 5 cycle, right? So it will be made up of 4 transpositions. This is a 4 cycle, so it be made up of 3 transpositions. And this is a 6 cycle, so it'll be made up of 5 transpositions. Now, 4 plus 3 plus 5 equals 4 plus 8 equals 12 is even. So it'll be made up as an even number of transpositions, and as such, D will be a even permutation. Let's do a counterexample, yeah, C. So this is a 4 cycle, so it's made up of 3 transpositions. And this is a 3 cycle, so it's made up of 2 transpositions. Therefore, it's made up of, in total, 3 plus 2 equals 5 transpositions, so it's odd. Yeah, find A1, A2. Yeah, it's probably nice to just prove in full generality. So, A1 of A2 all the way up to AN to the negative 1. Well, if we multiply A1, A2 all the way up to AN by AN, oh no, actually, AN minus 1 all the way up to A1. In this, it will send, for example, AN to AN minus 1, but then it will send AN minus 1 to AN. And then even going here, it will send A2 to A1, and then it will send A1 to A2. So this is equal to the identity. And using the fact that this is a group means that this is the inverse. So simply reversing the order that the elements appear in the cycle gives you the inverse. It reverses the permutation. Oh god, I meant to select. Alright. List all subgroups of S4. Nah. I'm good. I'm not going to be worrying about writing out a bunch of set theoretic computations, because that will just be pain for everybody. So, orders of elements of A7 show that A10 contains an element of order 15. Does A contain an element of order 26? I think what it will be for this, for example, A8, so like 8 factorial over 2, 26 is equal to 13 times 2. Yes, okay. So, if there's an element of order 13, there's a subgroup of order 13 in this. But that would contradict by what we will learn later as Lagrange's theorem. I'm just not even going to worry about proving it now, because it's literally going to be the next chapter we read, Cosets and Lagrange's theorem. That 13 is not in the prime factorization for this. And as such, there can be no element of order 26, since it would imply it has a subgroup of order 26, but that doesn't divide the order of the group. Alright. Oh gosh. Let have order and if diagonals of a cube. This is kind of important, but at the same time, it's really not. For these, this simply comes down to like, Sn is not abelian for n greater than 3, as long as we can show that there are 2 non-abelian elements, or elements A and B, such that AB is not equal to BA. in one permutation group or one alternating group, it will be in the case for all the further ones. And then it's just a case of showing that, first of all, we know that a sub 3 is congruent to the integers mod 3, which is abelian, or isomorphic to the integers mod 3. So we know that group's abelian. For n equals 4, you can explicitly compute that, but no, actually, for n equals 4, yeah, you can find a non-abelian set of elements. But that's like pure dreadful computation, which is something that I don't feel like is that great for a stream. Like, getting the true feel for this is just something you do for your own. Okay. Let's see, be a cycle. Yeah, for this is just kind of what I showed earlier, and the fact that at most a cycle in Sn is a n-1 cycle, or is a n cycle. So as we showed earlier, it can be written as n-1 transpositions. That sigma can be plus n-2 transpositions, which is the case that we have 2 cycles, so we like do that same process twice. Okay. Oh, actually, this is like, nah, okay. Let G be a group and define a map lambda G from G to G by lambda G equals Gi. Prove that lambda G is a permutation of G. Ooh, this is very good. Okay, so we define lambda G. So given G and G, we define lambda G from G to G by lambda G of G prime equals, in this case, let's call F multiplication GG prime. Now, for this, what is important to note is that lambda G to the -1, lambda G equals lambda G to the -1 equals ID of G, which by basic set theoretic ideas shows that lambda G is a bijection because it's an isomorphism in the category of set. And like fundamentally that's how we define isomorphism in set. Which implies that because it's literally just a bijection, a 1-to-1 and onto, that lambda G is a permutation. So fundamentally, lambda, like the composition of any element of a group by one element, this is why whenever we've been looking at a Cayley table of group, every column and every row contains every element. It's a representation of the fact that multiplication on the left or on the right by something is just a permutation. And yeah, you can do a similar thing for right list. Also, yeah, I should quick prove this. Lambda G to the -1, lambda G of H equals G to the -1 G of H equals H equals ID of H, IDG of H. Alright. Prove that there exist n factorial permutations of the set containing an elements. We already proved that previously. You basically show that any permutation can be represented as a permutation that fixes n-1 elements and then swaps around the nth element. And the set of n-1 by induction, you can show that's n-1 factorial. And then you multiply it by n possible places that your nth element can go. And then it's like n-1 factorial times n equals n factorial. So an inductive argument will prove 28. The center of a group G is the basically abelian subgroup of a group, kind of. There's something more specific that I don't know if it's gone into already. I don't think so. Called the commutator, but I'm not going to worry about it for now. This is kind of cool. There is something here, the idea of conjugation. And talking about has a relation to something called normal subgroups and quotient groups. But I'm just going to leave it teasing there, and I'm not going to go any more into detail, since eventually I do plan to cover that. Alright. Oh man, we are at the end already. God, this was a surprisingly short stream. This chapter was way shorter than I expected it to be. Alright, so same as f(x), we will let's find the orbit to be the set of y, the orbits to each of the elements. The group H is transitive only if some x and x. Ah, gosh. Okay, I'm debating this because this is kind of cool, but this is literally what is covered later on. Oh no. I'm going to just, for now, I'm just not going to worry about this. Yeah, I mean, like, there's not really much else to do. Because this is one of the main bad boys. This will make a lot of things start, like, really to pop. While permutation groups are kind of just, like, a leading up to this. Actually, let's do one of our normal table of contents previews. We'll be wind down stream surprisingly short tonight. Also, I should double check that they actually do have the group actions chapter. Since if they don't have the group actions chapter, that will be kind of embarrassing. Considering I'm like remembering so distinctly that chapter being in here. If it decides to load, okay. Oh no. Internet's having a fun time. Computer, please work. Yeah, wait, give me a second to reload the page. Refresh the page. Interacting. Also a reminder, in case you want to go through the book yourself, the book is freely available. If you look up the book, Abstract Algebra Theory and Applications, the free downloadable book is up there as a output of the Open Textbook Initiative, which is really awesome because these books should not be locked behind restrictions. It's very dumb and makes learning math unnecessarily hard. Okay. Cosets and Lagrange's theorem, Introduction to Cryptography. This will be my weak point. This will actually be genuinely kind of hard for me. Algebraic coding theory. This is also another one of my weaknesses, like applications. I'm specifically weak at. Isomorphisms. This is where I'll be in my element, and I'll probably try to introduce some category theoretic notation. Normal subgroups and factor groups, homomorphisms, matrix groups and symmetry, the structure of groups, finite abelian groups, solvable groups. This chapter is going to be definitely one. Group actions. Group actions is a fat chapter, and it does exist, yes. The CeLo theorems is going to destroy me. Rings, not an insubstantial chapter, nearly 20 pages. Polynomials, integral domains, lattices and Boolean algebras. Oh, this is like over 20 pages. Actually, not over 20 pages. I can't count. It's a substantial amount. It's going to terrify me. The algebra of electrical circuits. Oh no. Vector spaces, definitions, for example. This is going to be basically kind of like abstract algebra view of vector spaces and generalizing vector space constructions. And fields, finite fields, and Galois theory are going to be killers. Like if we go jump ahead in advance and look at Galois theory. The first things we have are like field extensions, the set of all automorphisms as a group of composition of functions. And we have basically talking about groups on other algebraic structures defined in terms of groups, like groups over those groups. It gives us more information. But anyways, I'm getting tired. I had marching band practice today. I'm gonna have marching band tomorrow. And I did most of what I actually wanted to do, most of anything that was cool. So, I guess I'll just do my normal awkward end of stream thing. Dang, not even an hour and a half. Kinda surprised, but at the same time kind of happy. So I guess thanks for tuning in. Have a nice